So what I've got up here, because I'm me, I like to use Excel to model things. So what I did was, I'm breaking the law a little bit here. I'm using Excel's randomizer to illustrate the iPod's randomizer. So what I've done is I've created a field of 50 songs being a random number picked between 1 and 10. So in other words, each one of those cells is a random number picked between 1 and 10. And each one of those would represent one of the songs on the iPod. As Di hit the shake to shuffle, you would then hear, so song 1 was Pat Benatar, song 2 was whatever song 2 was, song 10 was Run DMC. Doesn't matter which song was which, that's just how I labeled them and then when I put the numbers in front of them. So every time I press F9, essentially, we're redoing the experiment that Di just did. So there's 10 more. There's 10 more songs. Excuse me, 50 more songs. 50 more songs chosen from 10. There's 10, there's 50 more, there's 50 more, there's 50 more. Notice what happened here. We didn't hear track 5 at all. I forget what track 5 was, but we didn't hear it at all. We didn't hear it at all. Now, what I want you guys to do is I want you to watch those p-values up there. I know we haven't talked about this p-value yet. We're kind of going out of order a bit. I want you to try to come up with which hypotheses we're going to test based on that p-value. Now, what do you know about p-values? When they are small, which hypothesis do you believe? The second one, the research one. That's going to be your claim, right? That's going to be the claim we're trying to test. Look for a small p-value. I'm going to go pretty slowly until we find one. That's getting pretty damn close. That's almost 6%. I'm going to sneak under. Notice how this one looks compared to the ones that aren't small. See if you can see a pattern. Okay, there's a big one. There's a big one. Big. Huge. I wish I could go back. I shouldn't have hit go so quickly on that one. Okay. Notice big, and we're missing track 7. Interesting. Interesting. Big. Huge. Almost 100%. Okay. Big with a gap at 7 again. Almost 100% again. Are you seeing any kind of a correlation between the magnitude of how big and the size and what those bars look like? Any theory so far? Please, keep it going.
It seems like it's bigger when it's more evenly distributed.
Love that. When the bars are more uniform, that p-value tends to be higher, towards 100%. It doesn't have to be uniform to make it big enough to be bigger than 5%, but when it's close to 100%, the bars are getting, if you will, close to uniform. That's what they would be in a perfect world, wouldn't they? They'd be perfectly uniform. 5, 5, 5, 5, 5, 5, 5, 5, 5. That's over time, long term. But we're seeing a short term here. Okay, there's a half, 81. So far, what Kendra's saying, that's getting pretty small. Look at that one. Now look at the variance. That one song, track 5, got played 11 times. And then you had a bunch that, because that one got played 11, some other ones had to suffer, and they suffered across the gamut there. Very interesting, very interesting. All right, there's a 5.8% again. So what does it look, if we take what Kendra said, which is 100% correct, when the p-values are large, which means you have to believe the null hypothesis. If the p-values are large, right, you believe the null hypothesis. If that's the case, which of the two beliefs should be in the null hypothesis? That it's being random enough, or that it's not being random enough? What do you think? If this is getting close to 5%, it's getting close to being below 5%. Are these bars roughly the same height? No, not at all. Not at all. So bars that are becoming different heights implies a small p-value. What do you think bars being different heights implies about randomness? Is it being random if the bars are vastly different heights from each other? Or is it not being random? If you look into an extreme case, bars being vastly different heights implies it's not being random enough. We've missed the clumping. Check it out again. Okay, there's a p-value about 32%. Now, you might say, that looks just as vastly different as the last one we just had that had a small p-value. And my claim is it's not as vast. And we're going to measure that soon. We're going to get into the nuts and bolts soon. But the first thing I want you to understand is, let me click through again. Let me get a small one again. When you get a small p-value, it's tough. And you'll see why it's tough momentarily. There's a very small p-value, less than 5%. you've got bars that are vastly different heights from each other. In other words, remember how I started this off when you're flipping a coin, heads and tails, clash, Johnny Cash? If you clump too much, that's as non-random as not clumping at all. So what's happening here is we're clumping too much. We've crossed that threshold between clumping too much and clumping just enough versus not clumping at all. So let's get some unofficial hypotheses written down first. Unofficial hypotheses written down first. H0 versus H1. Big p-values, as Kendra said, I love what she said. Big p-values mean the bars are about the same height, which means the randomizer is working. So H0 is going to be that the randomizer is working. I mean, if you think about it, when Apple came out with the iPod Shuffle, is the first thing you said was, BS, I don't think it's working. No, you probably didn't. You probably said, oh my God, Apple made a new product, I have to go buy it now. And it sounds cool because it shuffles. You probably didn't come out swinging from the gates, guns drawn and blazing. You probably said, yeah, it probably works just fine. There's no reason to think it doesn't work. But then the data started creeping in and people started making claims that the randomizer wasn't working. Good. That the randomizer's not working.
Is that how we should write it on the data sheet?
No, well, I've got a mathematical way of writing it, but I wanted to make sure before we saw that, I wanted to make sure you knew which hypothesis was which, Mikey. Where the it's not working goes. Should it be a null or should it be a research? Okay. Mikey's question is a great one. Are there hypotheses that are numerical? Absolutely. Absolutely. Now the first thing, grab a template if you don't have one. Let's start slugging through it. Because I wanted to make sure this was guiding our discussion before we started into it. Which variable are we going to test? What do you think? If your gut was guiding you, which variable do you think we should test?
Proportion.
Definitely. Why?
Because it's like a 50-50 chance.
Boom!
You read.
Can I go 10, 10, 10, 10, 10, 10, 10, 10, 10, 10?
Yeah.
Versus 50? Is that okay, Mel?
Yeah.
Because you either hear a song or you don't. Correct? But the problem is there's 10 of them. That's what makes it interesting. See, it's how many songs, how many times did you hear this track out of 50? How many times did you hear track 2 out of 50? How many times did you hear track 3 out of 50? It's out of 50, out of 50, out of 50. Some of you might say, well, yeah, but it's an average number of times. Like, sure, you can make it that way, but it's still, did you hear it or did you not hear it? That's the kicker. Did you hear it? It's still binomial from track to track. But it's multinomial because there's more than 2 of them, and that's what makes it interesting. At least in my opinion, that's what makes it interesting. That's what makes it interesting. This is taking a coin flip to its next plane of existence, if you will. If a coin had 3 or 4 or 5 or 10 sides. Yes. So I definitely think we should treat this as a proportion. Yeah. Now, how many variables do you have? Holy crap, you have 10 of them. Now, I didn't give you enough space to write 10 variable definitions out. So let's use some clever shorthand. P1. What's P1 going to be? Say that again. Percentage of time?
That song number 1 is.
Exactly. Percentage of time that you hear track number 1. What's P2 going to be? Percentage of time you hear track 2, and then dot, 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 down to, goodness, an email's coming in, dot, 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 so you get to the percentage of 10, which is going to be the percentage of time that you hear track 10, dot, dot, dot. So just kind of, if you will, just fit it in space. You don't have to list every single one out. That's not important. The important thing is to know what variables you're testing. You are testing 10 of them. Holy crap. 10 variables. And you can test as many as you want. You can test 20, 30, 40. If I actually used my iPhone right now to test randomness in the iPhone proper, I think I'd have hundreds of them, because I have hundreds of different artists in my phone right now. And that's okay, because statistically we can do that with this, what we're learning right now. I actually had a student email me last fall from Spain, because she had an iPhone like this one. And she had too many, the same exact thing. She's like, I know better than this, but I think they're clumping too much. Because she heard, I forget which 2 artists. I never heard of them before, but she had like a boom, 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 and there was a small chunk of those artists within a 1,000-song playlist. And she was concerned about that. More on that later. But it was interesting that our guts often guide us the wrong way. We think something's not being random or is being random when it either isn't or is. So good.
So could random be defined as potentially having?
Of course it has to! You've heard of this. You've heard of the infinite monkeys theorem. Maybe? Infinite monkeys theorem? Have I talked about this before with you guys? Take it, last term, take an infinite number of monkeys. Put them in a room, give each of them a typewriter, and let them pound away. Eventually, you will get the complete works of William Shakespeare from one of those monkeys. Because that would be a clump, wouldn't it? That would be a certain clump. To be or not to be, comma. That must be somewhere in there. But not only that, but everything else from whatever the hell piece of literature that comes from, which I don't remember. Yes, you have to. If you let those monkeys type long enough, infinity, somewhere in that clump is going to be the complete works of William Shakespeare. Somewhere in that clump is the complete works of Stephen King. Somewhere in that clump is the complete works of Barbara Kingsolver. But you have to wait for infinity. That's a long time, right? And that was my point to the student was, that clump was bound to happen in your playlist. I was like, was that a brand new playlist you just started and hit play? And she's like, oh my God, no, I listened to it for 3 years. Well, then you were due. It's got to be in there somewhere. It just took you a while to get to it. You're absolutely right, Di. The question is, can you measure it in a discrete chunk of the playlist to test for randomness? Is that fair? Great question. Great point. Great point. It kind of is the point of all of this. Good. All right. Now, Mikey, let's answer your question. Okay? Because his question was, how about the hypotheses? So what are the hypotheses actually going to be? Well, let's start with the randomizer's working. Because I think that's the easiest one to test. What does it mean if the randomizer's working? What should this be equal to? What should P1 be equal to? 5 songs out of 50. Let's keep it with percentages, if that's okay? So, careful. 10%, right? 10%. 5 songs out of 50 should be 10%. Now, assumed there's a margin of error around that too, correct? There's definitely a margin of error around the 10%, but that's what the test will take care of, is that margin of error. So in other words, the randomizer's working implies that P1 equals 10%. How about P2?
Same.
How about P3? Yes. They're all going to be 10%. All of the P10. It's a uniform distribution in theory. In theory, it's a uniform distribution. You should hear song 1 the same proportion of times you hear song 2, the same proportion of times you hear song 3, the same proportion as you hear any of the songs on there. On average over time. Clumps notwithstanding, which we'll get to measure those too. Cool? What would the opposite of that be?
Less than 10%?
Or more. Right? So, this is tricky because there are 1,024 ways to talk about 10 discrete values and where they are, whether they're equal or not equal to each other. This is one of the 1,024. The other 1,023 are made up in here. And that is prohibitive to write all out. So the way I like to think about this is at least, this is going to be not too mathematical, but I think it's easier this way. At least one of those proportions is off. At least one of those proportions is off. And if I say off, Mel, that takes care of less than or greater than. It's just different. But we're just testing to see if it's not equal to 10%. Because clearly, hopefully you understand, if one of them is too high, some of the other ones have to come down low to make up for that, to balance it out. But the question is, if I just talk about it being off, that means it's off out of a margin of error from 10%, enough to arouse suspicion. At least one. It might be just 1, it might be 2, it might be 3. Hell, it might be all 10 of them. It might be all 10 of them. Maybe you shuffle the thing 50 times and you get 50 Clash songs and nothing of anything else. If you're a Clash fan, you're stoked. If you're not a Clash fan, you wonder what the hell, where's my Anthrax? Well, my Anthrax, it's in your Mad Cow. Fair? So that either they're all equal or at least one's off. That takes care of everything. Everything. It's a little less mathematical, but I think it's easier, Mikey, to write it out like that. Cool.
I would think that it'd be actually virtually impossible to get 10% equal each time.
On average over time, that's what 10% means. That's what a probability of hearing a song 10% means, is that on average over time. Now 50 is a snapshot of over time. But that's what the definition of, like, when you flip a coin, 50-50, It's impossible to set a number of trials and get exactly 50%. But the idea is it within a margin enough of 10%? The higher the number of trials, the tighter the margin. You're absolutely correct, Melanie. I would be suspect, as a matter of fact, hold that thought, because the distribution we use actually nods to that exact thought. It's almost impossible to get exactly 10%. And the mathematics will support that. But the thing is, it's not exactly 10%, is 10% enough? Is it 10% enough within a margin? And that's what this takes care of. Now, can anybody think of one way of testing that right now? Can we use tools we already have? Say yes.
Probably.
Or probably. Good. Can we test it right now? Say, give you a hint. Could we run a 1 prop Z int? We could theoretically. I mean, hell, you know that each proportion should be 10%. So you could run a proportion interval around what you saw. Let's take a look at this real quick. Real quick, you could do it this way. All right, so let's go over here. Okay, good. So let's just test Pat Benatar. So here's an old tool. Tests 1 prop Z int. 1 prop Z int is down there at letter A. We haven't used this in a few weeks. Let's build the interval around what happened with Pat Benatar. I put the data up there on the left board. Pat Benatar was song 1. We observed Pat 3 times out of 50 trials. Is that enough to believe she's happening 10% of the time? We can calculate. Take a look. What do you think? Is there any reason to doubt that she is happening 10% of the time? None whatsoever. What number's in that interval? 10% is in the interval, right? Now, this is a bastard move I'm pulling right now on you guys. I apologize. One of my confidence intervals. You totally can see that 10% is in this interval, which means there's no reason to throw out the fact that she's happening at 10% of the time. Fair enough? McKenna, go!
No, I was just saying 10% sure at the high end of that.
It is, but remember, that's random fluctuation. It's in the interval or it's not. Make it binomial, I see what you're saying. That's because she's below it. 3 is below 5. 5 would have been perfect, of course. And McKenna's got a point that 10's at the high end. It's almost on its way out, right? It's almost on its way out. As a matter of fact, the one that looks like they're on their way out are track 10 only happened twice, right? And track 5 happened 8 times. Those are the most extreme cases, yeah? Maybe we should take a look at those. What do you think, huh? I think so. Okay, 1 prop Z int. Let's do 2 out of 50. This is like Pat Benatar, but a little more extreme because we didn't see enough of them. Is that a problem? Looks like it, because 10% is not in that interval anymore. So now, McKenna, your point is well taken, is it's out of the interval. We can retest 8, but there's no reason to, because 8's going to be 2, because 8's going to be the other end of it. Is anybody bothered with what we're doing right now? We're cherry picking the ones that are extreme, which is not that necessarily a bad idea, but is anything going on right now with our results if we're doing this one at a time like this?
Yeah.
The age-old problem of?
On average.
What are we doing on average over time if we do them one at a time like this? What we always have a problem with if we try to do these multiple variables one at a time. We are reducing the confidence. Thank you. We are reducing the confidence. How bad is it going to be? We can do this for every single one of them, can't we? Every single one, we do it 10 times. The problem is, if we do that 10 times, we are down to about 60% confidence. That sucks. Now, unless we're going to avoid a type 2 error, in which case, what the hell, why not? But still, that's crappy statistics. You can't test at 60% confidence. You just can't. Because now the chance of being wrong in at least one of them is looking like a coin flip almost. So we need a test to do them all at once, which we're developing. I promise you we'll develop that. I promise you we'll develop this. We're in the process of doing it right now. Fair enough? But before we get into that, the errors, false positive, false negatives. False positive would be saying that the iPod is not being random enough when it actually is. Hopefully that makes sense to you guys, right? Saying the iPod is not random enough when it's actually totally fine. Crying wolf. Type 2 would be saying the iPod is random enough when it actually isn't. Do you guys have a vote for which one of these is worse? I mean, obviously it was newsworthy 6-7 years ago. Do you have any idea which one is worse?
Type 1.
Type 1? I think so. That's my vote too, because, Veronica?
Because it caused Apple to have to adjust things when it's fine.
And they already charge you enough for their products. Make them fix something that's not broken, they're gonna start charging $800 for a shuffle. Right? Exactly. Then if you make them fix... Now, we'll come back to that actually, we'll come back. I believe, it's my opinion too, I believe a Type 1, first of all, this is pretty frivolous. So we call it first world problem, of course. This is pretty frivolous. But I do believe a Type 1 would be worse because it would force Apple to potentially deal with a problem that doesn't actually exist, thereby passing the cost on to you, the consumer. Again, first world problem, but nonetheless, I think that, my vote as well, my friend, my vote as well. Now, here's the catch, what we have to do now. We can't test this the way we're used to testing it, because there are too many variables. If you think about it, the way we just tested that garlic, the garlic versus placebo, we simply took P1, P2, subtracted them, and looked for a difference. We can't do that with more than 2 though, because if you subtract more than 2, like P1 minus P2 minus P3, suppose that does get pretty far away from 0. The problem with having that many variables is you don't know which one's causing it. Does that make sense? If you simply try to fit this to that curve that we just looked at, you have too many variables at once. As soon as you get above 2, simply subtracting them, because an equation only has 2 sides. If an equation had 3 sides, this would be easy. Of course, we need an equation with 10 sides, which is 10 dimensions, which I can't picture, can you, or any of us for that matter. So the problem is, we can't do it the way we're accustomed to. But that's okay, because we can do it a different way. Here's the data. I've put the data on the sideboard over here. Let's back it out so you guys can see it at home. All right.